Okay, so this week we're gonna get into bias, calipers, and micrometers, and of course we're gonna take a look at the Excel, how to analyze your measurements. Okay, so one of the students need to review the introductory statistics, and you should have taken the level 1 stat. I believe is a course that you have to take in our major, but if you haven't taken it, I can review this for you. So for this lab 4, you'll need to know what is mean. Okay, so every time we do the measurement, you're gonna get the data set, and we call that a set of data. Yeah, and we usually try to find the center of that measurement, and finding the center of the measurements, and we call it the center of the data is actually the mean of that data set. Okay, and basically we're just trying to find the center of all of your data that you gathered from your measurements. Okay, mathematically you're gonna add all of the measured data, and we call them data values, and then we're gonna divide that sum by the number of the data values. Okay, so if you think about it, the mean of a data set uses every data value, so one extreme of a data, it can really change the mean drastically. Why? Because the mean depends on every value in your data set. Okay, we also have other measures of the center. Mean is not the only one, so we have like a median. Okay, we also have like graphical measure of the centers. We have curve, okay, like the normal curve measure of the center. But if you think about the sample means, okay, means that drawn from a sample population, they're usually they tend to vary, okay, less than other measures of the center. Like we also have population mean. Okay, so population mean is actually greater than the sample means, a little bit, not a lot, but a little bit. So the variation, and you're gonna come across many times that we talked about variation. Okay, we like to do the sample means because they vary less. So variation, if you have not much variation, that's a very good data. Yeah, and it's one of the reasons why we favor sample means more than the population mean, because as you know, the mean every time you calculate it depends on the data set. Okay, all of the values in the data set. So if you have a sample mean, because it comes from a sample population, so the variation is less, okay, than other measures of the center. Now we can take a look at what's population data and then what's the sample data. So you're going to see this is a set of data. It belongs to a population. You can see how big, yeah, the population is, and it's always bigger data set than the sample data set, because the sample data set comes out from that population data set. We select, okay, a set of data out of this population, so the data set for samples is always less, okay, or fewer than the population data values. Of course, we have two mean we can calculate, because you have a two sample data and a population data. You have two sets of data, so therefore we can calculate two different means. Okay, very simple as that. So the general idea of mean, we have already defined it. the sum of all data values divided by the number of data values mathematically. Yeah, so just looking at all the data over the number of that data. Okay, of course you add them up. Yeah, you're gonna add all of the data values, and then we're gonna look at that total sum against the number of the data. Yeah, and that is your mean. So for sample data, we're gonna do the same thing, but we're gonna use a different symbol, so you can be able to differentiate which one is a sample mean and which one is a population mean. Yeah, so the sample mean is we use the x and then a little bar on top of it. So when you see the x bar, that is a sample mean, and we calculate the same thing. We're gonna take the sample data, all the values, add them up, divided by the number of that data. Okay, population, we're going to use a little mu like this. Okay, so that's a population mean, and of course the population data is a bigger data set. So if you want to calculate the population mean, what we're going to do is we're going to add all of them. Yeah, so the sum of all the data values in your population data set, and then divided by the number of data values in that population. Okay, of course we use a big N for the population mean and then little n for the sample mean. Of course here we define what they are. So x bar is a mean of a set of sample values, and simply we call it sample mean. And mu is the mean of a set of all values in population, and we simply call it population mean. Okay. Then another thing that you have to understand is range. We always say range, right? Range of data, range of the years, so and so. So the range of a set of data values is nothing but we're gonna do a subtraction between that, the maximum value and the minimum value. Okay, so if you have so many data in your data set, we're gonna take a look at the max value and the min value, which is your minimum value in that data set. And then you're going to subtract the minimum value out of the maximum value, and you're going to get the range of that data set. Yeah. So range, it uses only the maximum and then the minimum data value. It doesn't use all of the data like in means. Okay. So therefore, range is very sensitive to extreme values. Extreme meaning like the maximum and the minimum. These are the extreme value. Okay, mean is a different thing because mean is using every data inside of that data set. So range it uses only the maximum and minimum value. It doesn't take every value into account, and it's very important. Okay, I already told you about that, and therefore it doesn't truly reflect the variation among all the data values. Okay, range again depends only on the max and the min, and then we're going to put it into a mathematical expression. So range is equal to maximum data value, and then minus we subtracted the minimum data value. Yeah. Then we have sample standard deviation. So standard deviation is nothing but it's just a measure of how much data values deviate away from the mean. It's just a measure of how far it is from the mean. Okay, so all the data, so let me draw that for you. So let me see. So if you have like a data here and data there, and then data here and then here, so you have all the little data in your data set. Okay, and then of course at one point you're gonna get calculate the mean, and let's say your mean is around here. Yeah. So now we have, if you want to understand how far away this data is from that mean, okay, and this distance, see that, and that deviation is called the standard deviation. Okay, so the red line is mean, and this is the target data or interested data, and we want to know this data, how far is it from the mean, and this deviation we call it the standard deviation. Okay, and these are all the data. So little green marks are all the data. The red line is your mean. The blue line right here is your standard deviation. Okay, so that's a measure of how much data value deviate away from the mean. And of course, we're going to use little s, okay, which is sample standard deviation. Since we have two mean, one is a sample and the other one is a population, we're going to have two standard deviations, yeah? But now let's concentrate on the sample standard deviation because sample mean doesn't have a lot of variation, yeah? So it's a very good way to represent the population. So if you have a larger value of standard deviation, then you have a greater amount of variation, okay? Okay, mathematically, how we're going to calculate the sample standard deviation, which is denoted by little s like that. We're going to have a square root, okay? And inside of the square root, what we're going to do is we're going to get the sum of the square. And what kind of sum of the square we're getting? We're getting the sum of the square of, all right, x minus x bar. So this means that, okay, this is your data, this representation mean the data value deviated from the sample data mean, okay? But this is your sample mean, and we are measuring how far away this data is from that sample, yeah? And then we're going to add them up, meaning like you have data x all the way to data n, yeah? So I should actually write here, it's going to go n equal to 1 all the way to x, yeah? This is a set of the data, it's not just one, okay? Because you have a sum here, so we're adding x1 all the way to x equal to n. Of course, we'll have to get the square, so that's just trying to find the entire standard deviation of that data set, okay? And then of course, so this is n minus 1 is your degree of freedom, n is your number of data, yeah? And this little x is your data value, and then this x bar is your sample data mean, yeah? So square rooted sum of x minus x bar, the whole square, divided by n minus 1 is going to give you your standard deviation. Of course, in the lab, you're going to use your Excel. You don't really need to calculate this by hand, okay? Everything is very automatic calculation for you since we're using the Excel for data analysis, okay? It makes things very easy for you. The only thing is that you have to choose the right standard deviation because we have mean for the sample and we have mean for the sample, okay? So for sample standard deviation, you're going to choose the correct Excel formula, yeah, for the sample standard deviation. So that's the only thing you have to be very careful of, yeah, when you use Excel for analysis. We can calculate the sample standard deviation with two different formula. So I have already shown you the very first one, yeah, and this is a second formula that we can be able to calculate in this way. So what's the difference between the first and second is the first formula is using the sample data mean, and the second one is not using the mean at all, yeah. So it reduces one of the calculation, meaning like you don't have to calculate the mean before you calculate the sample deviation. You can go straight from all of the data values, yeah. All you have to do is number of data and then calculate the degree of freedom, yeah. Then you're gonna have your data value, square it and sum it out, minus you're gonna have the sum of x, okay, and then you're gonna square it. This is different from that, okay? Why? Because we first square the x here. Here is we sum the x and then square it, okay? Very different thing. So just make sure that you understand this, okay? This is your sum is this, and then you're going to square it. Okay, this one is you square the x first before you sum it. Yeah. And don't make a mistake, because you can apply the exponential rule here, because this isn't the exponent. Okay, this is actually sum. Yeah, sum has its own bracket, so you don't do like, oh, this is the exponent of x and I can just go in and multiply 2 and 1. You can't do that, because this bracket isn't for the exponent. This bracket is for the sum. Okay, and of course this is definitely an exponent, it's straight up. Yeah, so do not make a mistake around here. I think a lot of students make a mistake around that, because they mistakenly take this parenthesis as the square, yeah, square of the exponent. But actually this parenthesis belongs to the sum, yeah, meaning like you have x1, x2 all the way to x equal to n, and you have to sum that up first and then square. And then we'll get into population standard deviation. Okay, population standard deviation is the same thing as in a sample standard deviation, because it's just a measure of how much data values deviate away from the mean. And of course, in population, we're going to use this little symbol sigma, yeah, and that's your population standard deviation. And it is a parameter denoted by little symbol, again, sigma. And you definitely need to differentiate, yeah, the standard deviation found from the population data is a parameter. Okay, for sample, I don't know if you recognize it, it is a statistic, which is your number. Yeah, the standard deviation found from the sample data is a stat, is a statistic denoted by S. It's not a parameter. Okay, parameter is different from the statistic. They're totally different thing. This is just number. Okay. Or we can also say, since we're doing the measurement, that this statistic is a measurement. Now, parameter is a very different thing. And this, okay, parameter is actually limits, okay? So for sample, standard deviation is a measurement. And for population, standard deviation, all right, it is a limit, okay? Even though they're the number, but they define a different thing. So just be very, very careful about it. Alright, so how are we going to calculate the population standard deviation? We're going to do the same thing, square root it. Your sum of x minus mu, which is your population mean, okay? That's your deviation from that mean your data is, yeah? That this data, of course, belong to the population or the sample. And then, of course, after you add it up, you're going to square that up, yeah? And then divide it by the number of population data is going to give you a standard deviation. Again, you don't have to remember this in our course, because we are using the Excel, yeah, standard population standard deviation has its own formula in your Excel sheet, and we will come to that. Then the next thing you have to know is a confidence interval. It's just an interval. It is in the name. Okay, interval is just a range. Your range always has the minimum and the maximum. Yeah, and range again is you are subtracting the minimum from your maximum. Yeah, don't forget these things. Or an interval, and of course, if that's the interval, you're gonna have a values. Yeah, and that values we're gonna use it to estimate the true value of that population limits. Again, on population parameter. Yeah. And confidence interval, you cannot be able to get it out of a definition, yeah? Because it refers to the set of the data and the nature of the data and the meaning of the data. So this depends on what type of data are you measuring or are you dealing with, yeah? So, but right now you should understand that it is an interval that we're very confident that whatever we're measuring are in it. Yes, so that's a kind of understanding you should get when you think about the interval. Meaning, I'm very confident of my data set in this interval, and that data is going to definitely represent what I am measuring about. Yeah, it's called the confidence interval. And of course, it is abbreviated as CI. So C for confidence and then I for interval. Mathematically, we're going to calculate this way. Since it is an interval, you have max and min. So therefore, you have your plus and minus again. Yeah. So every time you see plus and minus, you know that you're dealing with limits. The upper limit and a lower limit. Yeah. Upper for the plus and the lower for the minus. So here we're going to deal with our sample mean. Yeah. And that's your average data, which is your data mean. Here, since it is x bar, we're dealing with the sample, yeah, and this little t represent it just a number, yeah. Statistic meaning is represent a number, a standard number that we're using from the table. And S is your standard deviation, and then your N is your number of data. Of course, don't forget to square root it. So you're gonna time T and S divided by square root of N. Yeah, add that minus that from the mean is going to give you that interval. Yeah. Okay, and we have confidence level. Since we feel very confident that our data is going to be from this end, okay, upper end to the lower end within the interval. But how confident are you? Yeah. So the level of confidence is telling you, are you 100% confidence, 90% confidence, or 95% confidence, 99% confidence, right? Definitely you can never be confident about 100% full, yeah, because we always have a system or inherent error with our instrument, with our hands, right, with our operators measuring the part. So therefore, we can only go all the way to maybe 99.99% confidence, yeah? Okay, so when you take a look at the confidence level, we're talking about the probability, yeah? So if you have like a 100% probability, we usually write it 1 as abbreviation, and then minus alpha is a 100 minus the error. Alpha is your error. So if your system error, people error, human error, instrument error, if you minus that from 100% of perfection, okay, or the ideal one, yeah, you're gonna get your level of confidence. So if you have like 95% confidence, meaning you're subtracting, yeah, 5% of error out of 100. So you're gonna left with 95% confidence, yeah, interval, because you have a 5% error. So we have a different confidence level. We have 90, 95, and 99. So in decimal for 90% is 0.90. Decimal for 95% is 0.95. Decimal expression for 99% is 0.99%. So these are our corresponding error, yeah? So we have 0.10, 0.05, 0.01, yeah? Alpha is just a type 1 error. Okay, so this is error 10%. So therefore our confidence level is 90%. Our error is 0.05, which is 5%. So our confidence level is 100% minus 5%, which is 95%. In decimal, we can write it 0.95, yeah? Our error is 1%, yeah? So 100 minus 1% will give you 99%. In decimal, we can write it 0.99, yeah? Bias. So bias, we have bias in measurement, we have bias in instrument, we have bias in operator systems. So bias is nothing but statistically significant difference, yeah, between measured value, this is a value that you measure, and the actual, of course, the actual true value of your gauge. So researcher or the data taker, yeah, they sometimes intentionally or unintentionally bias their study. Unintentionally mean they make mistake, intentionally mean they are just cruel, yeah. And so bias their study by using a sample a sample that is biased. Yeah. So in some cases, researchers intentionally use a biased samples to make sure that their desired results are obtained. So making that happen, we don't do that. Yeah. In science, it's very important that you report as you observe, as you see, okay, as you noticed, and as you measured. Do not deviate anything. Otherwise, you'll be getting all wrong things, and the truth will be distorted. Yeah. So the sampling bias can seriously distort the results, and that can lead, of course, to wrong or misleading conclusions and very unethical. Right? Bias is unethical, so therefore we must avoid it, avoid doing it. Yeah. Okay, so degree of freedom, I have already shown you how to calculate. Is your number of your data minus 1 is going to give you your degree of freedom. Yeah, degree of freedom goes from 1 all the way to 20, depends on the number of your data, yeah, in your data set. Here is your confidence level. So this is your student's statistic table. Statistic mean nothing but just a list of numbers. Yeah, so you can see the number table right here. And of course, how we're going to read it, we're going to use our confidence level, either 80%, 90%, 95, 98, or 99% confidence levels, whatever you're calculating. Yeah, for your confidence interval, we use our level and the error. Yeah, and of course our degree of freedom, we can be able to read the number, and then we're going to put it right here when we calculate. Yeah, right there at the T. For your confidence interval calculation. Okay, so this is the very first video for your lecture for the lab 4, and it should be good, yeah, for you to be able to calculate everything that you need to know for your lab 4. Calibers and micrometers we have already gone over the past 2 weeks, and you can review if you need to the past lectures. For lab 2 and 3 is covering the they cover the calibers and micrometers. Okay, then of course we will get into your Excel review. Yeah, Excel is your TK 101 Excel review, and we will definitely go into that after this lecture. Yeah, that's it for today.